is the lecture for complex numbers. All right, in the previous lecture on simplifying radical expressions, our answers were usually real numbers, but we did have that one example in there. If you remember, we were asked to find it was the square root of negative 25, or simplify the square root of negative 25, or specify that it's a non-real number. And of course, the square root of negative 25 is a non-real number because there are no two numbers that when you multiply them together, when you multiply them with each other, equal negative 25. Or there is no number that when you square it equals negative 25. So this causes us a problem. Sometimes we need to continue calculations where we find ourselves having a negative radicand. Remember, the radicand is the number under the radical sign. We find ourselves in situations where we have a negative radicand under an even root. We're going to focus primarily on square roots, but this concept also causes problems with fourth roots and sixth roots and any even root. Okay? Well, if we consider the equation x squared equals negative 1, if we were to solve that equation, we would just take the square root of both sides, right? Take the square root of both sides, and the square root of x squared, the square root undoes the squaring, and we would find that our answer is plus or minus the square root of negative 1. It's actually missing there. I should add that. Plus or minus the square root of negative 1. And the square root of negative 1 is not a real number. There's nothing that when you multiply it with itself results in negative 1. So when we find ourselves in this situation, we introduce the concept of complex numbers, and in particular, we introduce the imaginary number to enable us to continue with our calculations. All right, complex numbers take the form a plus bi, where a and b are real numbers and I is the imaginary number, right? So the a here, this is just some real number. The b would be some real number. But this I right here is the imaginary number. And the imaginary number is defined as the square root of negative 1. So by definition, I equals the square root of negative 1, by definition. All right? So it follows then, if we square both sides of this, that I squared is the square root of negative 1 squared, right? Which of course is just negative 1, right? So the two definitions that we're interested in here when dealing with complex numbers are those definitions for I squared is the square root of negative 1. I'm sorry, I is the square root of negative 1, and I squared is equal to negative 1. We can also, well, it follows then that if we have some real positive number a, the square root of negative a equals I times the square root of a. Why would that be true? Well, we know that I squared is defined as negative 1, right? So if we make a substitution, we could write the square root of negative a as the square root of negative 1 times a, right? That's the same as negative a. And if we substitute this I squared in here for that negative 1, because we know that I squared is equal to negative 1, we could write this as the square root of I squared times a, which of course is the same thing as the square root of I squared times the square root of a, right? And the square root of I squared is just I, right? So this simplifies down to I square roots of a, where a is just any real number at all, any real number. All right, so there's a shortcut here. Whenever we're dealing with a negative radicand under an even root, we can continue to run calculations if we stick an I out front and drop the negative sign. Okay, stick an I out front and drop the negative sign, and this is why, because I squared is equal to negative 1. All right, let's look at a few examples of simplifying non-real numbers. Here we have the square root of negative 25 again. In the last lecture, we said, well, that's a non-real number, and we just left it at that. Well, now we're going to go a little further with it, and we're going to simplify that non-real number. Okay, we're going to simplify that non-real number by remembering that I squared equals -1, or the square root, let me write it this way, or I equals the square root of -1. Okay, and because that's the case, I can think about the square root of -25 as the square root of -1 times 25. Right, that's -25. And since -1 is I squared, I could rewrite this as a square root of I squared times 25. Okay, which is equivalent to the square root of I squared times the square root of 25. The square root of I squared, of course, is I, and the square root of 25 is 5, so it's I times 5, or in more proper form, we would write this as 5I, 5I, right? The shortcut here, when you see a negative radicand under a square root, drop that negative, stick an I out front, and then continue to simplify. So the square root of -25 would be I times the square root of 25, which is, of course, I times 5, or 5I. Okay. How about this next example? Simplify the square root of -50. Simplify this non-real number. Well, what we want to do is we want to remember, let's first of all make it real, all right? So we'll drop that negative and stick an I up front. So this will be equal to I times the square root of 50. Okay, now can we simplify the square root of 50? Well, remember, in simplifying radicals, we want to look for the largest perfect square that's a factor of that radicand. All right, well, 25 is a factor of 50. 25 times 2 is 50. So I could simplify this into I times the square root of 25 times 2, right? 25 times 2 is 50. The square root of 25, of course, is 5. So this can become I times 5 times the square root of 2, or I probably would write this as 5I square roots of 2, just to make that in a little bit better form. Okay, so complex numbers. These are just using the imaginary number to simplify non-real radicals. But sometimes there's a real portion to a complex number. When there's an A. Remember, it's A plus BI. We have an imaginary portion and a real portion. And there are several operations that we can do on complex numbers. One operation is to add complex numbers. With this example here, we're going to add the complex number 2 plus 5I with the complex number -3 minus 6I. To do that, we're simply going to be combining like terms, right? The real terms, 2 and -3, those are like terms. And the imaginary terms, 5I and -6I, those are also like terms, right? So we're going to first add the 2 and the -3. 2 plus -3 is 2 minus 3, or -1. This will be equal to -1. And then we want to combine those imaginary numbers. The imaginary numbers are 5I and -6I. Positive 5I plus -6I is going to be -1I, or -I. Okay, so 2 plus 5I plus -3 minus 6I is going to be -1 minus I. We just combine like terms. It's as if we're doing the same thing here. It's the same as if we're adding two binomials, right? When we're subtracting complex numbers, do you know what I like to do? I like to distribute the negative sign and drop the parentheses. When I do that, that helps me not forget that I'm subtracting the real number and I'm subtracting the imaginary number. So I like to do that. I like to distribute this negative sign and go ahead and drop the parentheses. So then this becomes 6 minus 2I minus -4I. That's plus, I'm sorry, minus a -4. So that's plus 4, and then minus 3I. Now I just have to combine my like terms. I want to add 6 and 4. Well, that's going to be equal to 10. Right? And then I want to add negative 2i and negative 3i. That's going to be negative 5i. Okay, so adding, subtracting complex numbers is really just combining like terms. We can also multiply complex numbers. When we multiply complex numbers, we want to think about it the same way that we do when we multiply polynomials, Okay, so if we're multiplying this purely imaginary number 5i with this complex number that has a real and an imaginary portion, 10 plus 3i, what we want to do is think about what we would do if we were multiplying a monomial, a one-term polynomial, with a binomial, a two-term polynomial. We want to do the same thing. Or in other words, what we want to do is we want to distribute this 5i. Right? So 5i times 10 is 50i, and 5i times 3i is going to be 5 times 3, that's 15, and they're positive, so say plus 15, and then I times I, that's I squared. Okay? So multiplying that wasn't too hard, right? Except that complex numbers must be in the form a plus bi, where a is the real portion and bi is the imaginary portion. Well, this is not in the right form. So I have to manipulate that a little bit so that it looks like more like a complex number. In other words, I need to get rid of this I squared. Well, we know that by definition, I squared equals negative 1. Right? So what we want to do here is we want to substitute that negative 1 in there for the I squared. Right? So this then becomes 50i plus 15 times negative 1. Right? Instead of 15i squared. Right? It's still not quite in the right form. Look, we should have the real portion first and the imaginary portion second, so we need to move it around just a little bit. 15 times negative 1 is negative 15, and that's going to be the real portion. So this is going to be negative 15, and then 50i is the imaginary portion, so that should come next, plus 50i. Okay? So you always need to rearrange after you do whatever operation you're doing on complex numbers, but in particular when we're doing multiplication, a lot of times you end up with an I squared. When you end up with an I squared, you want to make that substitution for negative 1 and then rearrange things into the proper format. Let's look at this other example. Here we have two fully complex numbers. There's a real portion and an imaginary portion in each of those complex numbers, right? So what we're going to do there is the same thing that we would do if we were multiplying two binomials. We want to multiply every term with every term, all right? So let's multiply the first terms, multiply that first term of the first complex number with the first term of the second complex number. 5 times 8 is going to be 3. All right, now let's multiply the first term of the first complex number with the second term of the second complex number, or 5 times 2i, that's positive 10i. Okay, now these middle terms, negative 7i times 8, that's going to be negative 56i. Okay, and then negative 7i times positive 2i is going to be negative 14i squared. Right? Now we need to clean this up a little bit, right? The I squared equals negative 1, so let's make that substitution. Put that I squared in there for that negative 1. Also, we have some like terms that we can combine. Look, we have two I terms here. We have positive 10i and negative 56i. Right? Maybe we'll do this at the same time. So let's see. We'll bring down our 40. We're going to leave him alone for a minute. Won't do anything with him. 10i minus 56i is going to be negative 46i. Okay? And then minus 14 times negative 1. Right? Replacing that I squared with the negative 1. Well, negative 14 times negative 1 is positive 14, right? So I can now combine, I've got some more like terms I can combine. I've got this last part here, negative 14i squared turned real, right? Negative 14 times negative 1 is positive 14. I can add that positive 14 to that 40. And then this will become 54 minus 46i. Okay? So multiplying complex numbers, you just think about them as if they're polynomials, right? You just think about them as if they're polynomials. And then if you have an I squared, replace it with -1 and rearrange and pretty it up, and there you have it. Just a couple more examples. Look at this one here. This is so tempting to distribute that I squared and just call this 5 squared minus 7i squared, isn't it? But that is not okay. Don't do that. Because of those parentheses, right? What we're doing here is we want to multiply 5 minus 7i with 5 minus 7i. We gotta multiply every term with every term, not just multiplying the first terms and the last terms. All right. So some of us have learned that FOIL acronym. If you've learned that, you can do that here. But we want to multiply every term with every term. 5 times 5, of course, is 25. 5 times -7i is -35i. You can do that again, -7i times 5, that's another -35i, and then -7i times -7i, that'd be a +49i squared, right? That I squared is -1. Okay, and there's like terms to combine. Let's start simplifying this or prettying this up a little bit, right? So this will be 25 minus 35i minus another 35i, or minus 70i, then plus 49 times -1, that's minus 49, and 25 minus 49 is -24. So this equals -24 minus 70i when I combine all my like terms and put it in the proper order. Okay, look at this last example over here. What does this look like? This is kind of interesting. It's almost the same complex number, except for the sign is different, right? Do you guys remember conjugates? When you're doing polynomials, remember what conjugates are? There's a similar concept going on here. These are complex conjugates. They're complex numbers. They're complex conjugates. When you multiply them together, you end up eliminating the imaginary number. Watch this. Let's multiply each term with each term. 5 times 5, of course, is 25. Then we have 5 times 7i, that's plus 35i. -7i times 5 is minus 35i, and -7i times positive 7i is -49i squared, right? Well, because they're conjugates, right, almost the same, just with different signs, because they're conjugates, we already know that the middle term is going to add out when we multiply them, right? These guys go away. Of course, I squared is -1. Make that substitution. So we end up with 25 minus 49 times -1, or 25 plus 49, which is 74. Isn't that cool? When you multiply a complex number by its conjugate, right, it's basically the same complex number, just change the sign, the imaginary portion goes away. There is no longer an I involved. And that's very important when we need to simplify fractions that have complex numbers in the denominator, because we cannot divide by an imaginary number. All right, let's look at a couple of examples practicing finding the complex conjugate. The first one is easy, right? 3 plus 2i. What is the conjugate? The conjugate is going to be 3 minus 2i. Same thing, just change your sign, right? 3 minus 2i. What if there's only one? This is interesting. What if there's only one term, though? What if there's only one term? What would the conjugate of 4i be? Well, it's really just anything with an I in it. Our objective here is to eliminate the i's, right? What about -5i? What is that conjugate? Well, when our objective is to remove an imaginary number in the denominator, if we only have the one term, we really could just multiply by I over I, or negative I over I. Let's look at a few examples of that. Dividing complex numbers involves having an imaginary number in the denominator, and then that's not okay, because how do you divide by something that isn't even really a number? The imaginary number, it's more of a concept. By definition, we said I is the square root of -1, right? But the easiest thing to do when you're simplifying a fraction with a complex number in the denominator, or when we're dividing complex numbers, is to multiply by the conjugate, right? So if we're multiplying by the conjugate to get rid of I in that denominator, the conjugate of -1 plus 3I is going to be -1 minus 3I, okay? But we don't want to change the value of our expression here, so we have to multiply the numerator by the same thing. We just want to multiply by this fancy one. We don't want to change the value of our fraction over here, right? So we're multiplying by -1 minus 3I over -1 minus 3I, right? So when we perform that multiplication, let's see, for the numerator, we're just going to be distributing that 8I, right? So 8I times -1 is negative 8I. 8I times -3I is negative 24I squared. Okay, now let's multiply the denominators. -1 times -1 is 1. That's our first term. -1 times -3I is positive 3I. Positive 3I times -1 is negative 3I. And then positive 3I times -3I is negative 9I squared. All right, when we simplify that, I squared is -1. So we have negative 8I minus 24 times -1 over, let's see, these I terms add out, right? So that's going to be over 1 minus 9 times -1. Right? Let's see. Negative 24 times -1 is positive 24. Remember, I need to have A plus BI form. So the real part comes first. So negative 24 times -1 is positive 24 minus 8I over 1 minus 9 times -1. That's 1 plus 9, or 10. All right. Now that is almost all simplified. There's no imaginary numbers in the denominator. But look at this. Every term, there are some common factors. I could factor a 2 out of the numerator and the denominator. So I could do this. I could say this is 2 times 12 minus 4I over 2 times 5, right? And then my 2's divide out. So I just simplified that a little bit more, didn't I? Now it's 12 minus 4I over 5. Now, is that in the standard form that we need to see for a complex number? Is it A plus BI? Not quite exactly. We're going to need to split that out a little bit. We're going to want to say this is 12/5 minus 4/5 I. That's a better form to write that in. A 12/5 plus B -4/5 I. Okay, another example down here. This one has a fully complex number in the numerator as well as the denominator. So it has a real portion and an imaginary portion in the numerator as well as the denominator. Well, to simplify that, we're going to multiply by the conjugate, right? So what's the conjugate of 2 minus I? I'm going to multiply by the conjugate of the denominator. That's 2 plus I. We don't want to change the value, so we want to multiply that by 2 plus I over 2 plus I. Okay, so let's see. We're going to multiply every term with every term here, right? 2 times 2 is 4, plus 2 times I, plus 5I times 2, that's 10I, plus 5I times I, that's 5I squared, plus 5I squared, okay? Over, let's see, 2 times 2 is 4. 2 times I is plus 2I. Negative I times 2 is negative 2I, and the negative I times I is negative I squared. Okay, let's see. Simplify that numerator. The I squared here is -1, right? and I can combine my like terms. Let's see. So 5 times -1, that's -5 plus 4. That's going to be -1, right? -5 plus 4 is -1. And 2i plus 10i is 12i, and that's positive. Okay. And the denominator, well, those I terms, they do add out, right? And then I squared is -1, right? So this is going to be 4 minus -1, or 4 plus 1 over 5. Okay? And if I should split that out to write that in the proper form, a plus bi, this is going to be -1/5 plus 12/5 I. Okay? One more example. What happens when we need to multiply two non-real radical numbers? What do we do with that? Well, you know, the temptation here is just to go ahead and multiply. Here's the temptation. This is not correct. Is to go ahead and multiply these and say this is the square root of -5 times -15, which of course is the square root. What is 5 times? -5 times -15 is 75, right? And then simplify it, right? It's 25 times 2 times 3, or 5 square roots of 3. So there's your temptation. I'm going to get my red marker and draw a big X through it. That's not allowed. So none of that is right. Why is that not allowed? These aren't real numbers. They don't follow the rules of multiplication. You cannot multiply non-real numbers. You've got to make them complex numbers first by introducing I. So what do we want to do here? Well, I squared is -1, right? Or we can take the shortcut, drop the negative and stick an I out front. Let's do the shortcut. So this then becomes I times the square root of 5 times I times the square root of 15. Okay, now I can deal with these. I can multiply complex numbers. I cannot multiply non-real numbers. I can't do any operations with non-real numbers. I always have to make them imaginary or complex first. Okay, I have to make them imaginary or complex first. All right, so we introduced I here. Now these are things that I can deal with. I times I, of course, is I squared, right? Square root of 5 times the square root of 15, that's the square root of 5 times 15, or the square root of 75. And I squared, of course, is -1, right? It's -1. So this then becomes -1, or just negative square root of 75, which simplifies, let's see, to negative, and then 75 is 25 times 3. Square root of 25 is 5. So this will simplify to -5 square roots of 3. Right? So if you tried to multiply these non-real radical numbers, or these complex square roots, if you tried to multiply these guys, you would end up with +5 square roots of 3. But we drew the big red X through that. That is not allowed. They're not real numbers. You can't multiply them. The actual answer here, not the real answer, but the true answer, right? The actual answer, when we multiply the square root of 5 times the square root of -15, is -5 square roots of 3. And without that negative, we don't have the right value here at all. Right? That ends the lecture on complex numbers.